For 50 years, we learned a simple rule in mechanics. There is no replacement for displacement. This was the golden commandment of the automotive world, a law written in iron and aluminum. A 2.0-liter engine was supposed to be the beating heart of a commuter car, a tool for efficiency, designed to get you to the grocery store and back with minimal fuel consumption. It was never intended to be a racing monster. But Toyota has just broken that law. They have built something that, mathematically speaking, should not last more than a single lap on the track without disintegrating. Yet, it endures. Today, we are going to open the patents and understand exactly how they bent the laws of thermodynamics to squeeze 600 horsepower out of a block small enough to fit in a backpack. To understand the gravity of this achievement, one must first look at the graveyard of failed attempts. Throughout history, forcing high horsepower into small displacements has always resulted in one of two things: massive turbo lag that makes the car undrivable, or catastrophic engine failure due to cylinder pressures that the metal simply could not withstand. The physics are brutal. To generate 600 horsepower from 2.0 liters, you are asking each cylinder to handle an explosion equivalent to a stick of dynamite, thousands of times per minute. The heat generated is usually enough to melt piston rings and warp cylinder heads. This is why the industry moved to electric motors or stuck with massive V8s for performance. But Toyota, a company known for conservative reliability, decided to do the impossible. They looked at the internal combustion engine and decided it wasn't dead, it was just sleeping. Hey guys, quick break because we need your help to validate this deep dive into engineering history. We are incredibly close to hitting 10,000 subscribers, and we need to smash that goal ASAP. If you haven't already, please hit that like button and subscribe. It makes a massive difference and helps us keep decoding these mechanical mysteries. Also, if you want to support the channel directly, check out the super thanks button below. And drop a comment letting us know where in the world you're watching this video from. We love seeing how far our petrolhead community travels. Now, let's get back to the blueprints. The engine in question is not just a tuned version of an existing platform. It is a clean sheet design that completely rethinks the relationship between air, fuel, and spark. When Toyota announced this project, many engineers assumed it was a hybrid-assisted figure, where the combustion engine did half the work and electric motors did the rest. They were wrong. The 600 horsepower figure is purely mechanical, derived from combustion. This creates a specific output of 300 horsepower per liter. To put that in perspective, a Bugatti Chiron, a pinnacle of engineering, produces roughly 185 horsepower per liter. Toyota has nearly doubled the efficiency density of a hypercar engine in a mass production prototype. The secret begins with the block itself. Traditional cast iron or aluminum blocks have limits on how much structural rigidity they can offer before they become too heavy. Toyota's engineers utilized a new casting method, hinted at in recent patent filings, which suggests a shorter deck height and a reinforcement structure that mimics the organic lattice found in human bones, maximizing strength while minimizing material. But the real magic isn't just in the metal, it's in the air. The biggest enemy of high-boost, small-displacement engines is heat. When you compress air to the levels required for this power output, the intake charge becomes superheated, which leads to pre-ignition or knock. Knock is the engine killer. It is the sound of the fuel exploding before the spark plug fires, shattering pistons. Toyota's solution to this thermal nightmare is a radical departure from standard intercooling. The blueprints reveal a water-jacketed exhaust manifold integrated directly into the head, but with a twist. They are using a split cooling system that runs the block at a completely different temperature than the head. By supercooling the combustion chamber while keeping the block warm for oil viscosity, they can run compression ratios that were previously thought impossible for a turbocharged engine. This allows them to ignite the fuel mixture with laser-like precision, extracting every joule of energy without detonating the engine. This is not just tuning. This is manipulating the thermal environment of the explosion itself. The mastery of temperature is only the first hurdle. Once you stop the engine from melting, you have to solve the problem of breathing. An engine is fundamentally an air pump. To make big power, you need to move massive amounts of air. In a 5.0-liter V8, the sheer volume of the cylinders does the work for you. In a 2.0-liter block, you don't have that luxury. You have to force the air in, and this brings us to the geometry of the engine itself. Historically, engines designed for high horsepower utilized a square, or over-square design, where the width of the cylinder, the bore, is larger than the distance the piston travels, the stroke. This allows for massive valves and high RPMs, screaming all the way to the red line. However, Toyota's new blueprint seems to contradict this racing heritage. Analysis of the technical specifications reveals that Toyota has opted for a geometry that favors a slightly longer stroke relative to the bore. In traditional engineering, this is a recipe for a low RPM truck engine, designed for torque, not horsepower. A long stroke increases piston speed, which increases friction and typically limits how fast the engine can spin. So why would they do this for a 600 horsepower racing heart? The answer lies in the physics of flame propagation. By lengthening the stroke, Toyota creates a combustion chamber that is compact and tall. When the spark plug fires, the flame front doesn't have to travel as far to reach the cylinder walls. This results in a faster, more complete burn of the fuel-air mixture. They are trading pure RPM capability for thermal efficiency, ensuring that every drop of gasoline is converted into pressure rather than waste heat. But a long stroke usually means the engine cannot breathe well at high speeds. This is where the patent filings regarding the intake ports get interesting. Toyota has redesigned the angle of the intake ports to create a violent tumble flow. Imagine water rushing down a drain. Instead of flowing smoothly, it is engineered to crash and swirl chaotically. Inside the cylinder, this turbulence mixes the fuel and air so thoroughly that the mixture becomes almost perfectly homogeneous. This allows the engine to run lean, using less fuel and more air, without causing the catastrophic knock we mentioned earlier. This high-tumble approach is what allows a long-stroke engine to act like a high-revving racing motor. Then comes the forced induction. To get 600 horsepower from 2.0 liters, atmospheric pressure is useless. You need boost, and lots of it. The standard industry solution is a massive turbocharger. A big turbo can move enough air to hit the power target, but it comes with a heavy price lag. You stomp the gas pedal, and for 2 seconds, nothing happens while the heavy turbine spins up. In a racing scenario, or even on a spirited drive, that delay is unacceptable. Toyota's solution appears to be drawn directly from their WRC, World Rally Championship, dominance. The schematics indicate the use of an electrically assisted turbocharger, a technology that bridges the gap between F1 and the road. This is not a traditional turbo. On the shaft connecting the exhaust turbine and the intake compressor, there sits a compact, incredibly powerful electric motor. Before the exhaust gases have even built up enough pressure to spin the turbine, the electric motor activates, spinning the compressor to 100,000 revolutions per minute in a fraction of a second. The result is instant boost. It mimics the throttle response of a massive, naturally aspirated V12 engine, but does so with a fraction of the weight and displacement. This system eliminates the physics of turbo lag by substituting exhaust pressure with electrical torque. Furthermore, the integration of this turbo system requires a block structure that can handle the immense cylinder pressures. We are talking about pressures exceeding 250 bar within the combustion chamber. For context, that is roughly equivalent to the pressure of the ocean at a depth of 2.5 kilometers. A standard aluminum block would crack or warp under this stress. Toyota's Material Science Division has reportedly developed a new alloy specifically for this project. It is not just aluminum. It is a proprietary blend likely enriched with trace amounts of scandium or zirconium, elements used in aerospace to prevent microfracturing under cyclic load. This material allows the cylinder walls to be thinner, transferring heat to the coolant faster, while retaining the tensile strength of steel. The engine is essentially a pressure vessel disguised as a car part. With the air forced into the engine by the electric turbocharger and contained by the aerospace-grade alloy block, the next challenge is control. Having high pressure is useless if you cannot precisely manage when it enters and exits the combustion chamber. This brings us to the valve train, the mechanical lungs of the beast. In a standard high-performance engine, the valves are operated by camshafts that are typically adjusted by hydraulic pressure, oil. When you step on the gas, a solenoid opens, oil pressure builds up, and the camshaft shifts its timing to allow more air in. It is a proven system, but for Toyota's 600 horsepower target, it is too slow. Oil is viscous. It reacts to physics with a slight, almost imperceptible delay. At 7,000 revolutions per minute, that millisecond delay is the difference between peak power and a misfire. Toyota's solution, detailed in their advanced engineering documentation, is the implementation of VVTIE, Variable Valve Timing Intelligent by Electric Motor. Instead of relying on engine oil pressure, which fluctuates with RPM and temperature, the intake camshaft is controlled by a dedicated, high-speed electric motor. This decouples the valve timing from the engine speed entirely. The computer can set the camshaft to a racing profile before the engine has even completed a single revolution. It allows for infinite adjustability, meaning the engine can switch from an efficient Atkinson cycle for cruising to a high-power Otto cycle instantly. The valves are performing a mechanical ballet, opening and closing with a precision that hydraulic systems simply cannot match, ensuring that the massive boost pressure from the turbo is never wasted against a closed valve. However, air is only half of the combustion equation. The other half is fuel. To generate 600 horsepower, you need to burn a significant amount of gasoline. But simply dumping fuel into the cylinder is a crude method that leads to unburnt hydrocarbons and washed-out cylinder walls. The challenge is atomization, turning liquid gasoline into a mist so fine it behaves like a gas. Toyota's engineers have doubled down on their D4S injection system, a technology that combines two distinct types of fuel injection. Most modern cars use direct injection DI, spraying fuel directly into the combustion chamber. While efficient, DI has a downside. It doesn't clean the intake valves, and at extremely high RPMs, the window to spray fuel is vanishingly small. For this engine, Toyota utilizes both direct injection and port injection simultaneously. 8 injectors for 4 cylinders. The port injectors spray fuel into the intake manifold, cooling the air before it enters the engine and cleaning the valves. The direct injectors spray straight into the cylinder at pressures exceeding 350 bar. The magic happens in the interplay. Under heavy load, the direct injectors provide a crucial secondary function, cooling. When liquid fuel evaporates inside the hot cylinder, it absorbs heat, a process known as the latent heat of vaporization. This drastically lowers the temperature inside the combustion chamber, effectively acting as an internal chemical intercooler. This cooling effect is what allows the engine to run such high boost pressures without detonating. They are using the fuel itself to fight the thermodynamics of heat. Then there is the issue of friction. Friction is the parasite of horsepower. In a 2.0-liter engine spinning at high speeds, the friction from the pistons rubbing against the cylinder walls can rob the engine of 10 to 15% of its power. Every bit of energy lost to friction is energy that doesn't reach the wheels. To combat this, Toyota has turned to surface treatments usually reserved for Formula One. The piston skirts are coated in DLC, diamond-like carbon. This is a nanocomposite coating that is incredibly hard and slick, reducing the coefficient of friction to near zero levels. The pistons themselves are not just coated, they are sculpted. The crown of the piston, the top part that faces the explosion, is not flat. It features a complex, computer-modeled shape designed to work in tandem with the tumble flow of the intake air. It acts as a ramp, guiding the swirling air-fuel mixture toward the spark plug. This ensures that the flame kernel, the initial spark of ignition, sits in the richest, most combustible part of the mix. By controlling the flame's location, they ensure the explosion pushes the piston down squarely, rather than wasting energy rattling it against the side of the cylinder wall. It is an obsession with efficiency at the microscopic level. Once the explosion occurs and the piston is driven downward, the engine faces its next critical challenge, evacuation. Getting the spent gases out of the cylinder is just as important as getting fresh air in. In a high-performance engine, exhaust gases exit the combustion chamber at supersonic speeds and temperatures exceeding 900 degrees Celsius. If you don't manage this flow correctly, you create back pressure, essentially choking the engine with its own waste. Traditional engines use external exhaust manifolds, those twisting bundles of rusty pipes you see bolted to the side of the engine head. But for this 600 horsepower application, Toyota deleted the external manifold entirely. Instead, the exhaust manifold is cast directly into the aluminum cylinder head itself. This is an engineering marvel known as an integrated exhaust manifold (IM). By burying the exhaust runners inside the liquid-cooled head, Toyota achieves two things simultaneously. First, it rapidly lowers the temperature of the exhaust gases before they hit the delicate turbocharger turbine. This protects the turbo from thermal stress, allowing it to spin faster for longer periods without seizing. Second, and perhaps more importantly, it warms up the engine coolant incredibly fast during cold starts. But the real performance benefit is in the flow dynamics. By shortening the distance between the exhaust valve and the turbocharger to just a few inches, the pulse energy of the exhaust gas is preserved. The gas hits the turbine wheel with maximum kinetic impact. However, a four-cylinder engine presents a specific problem for turbocharging due to its firing order: 1-3-4-2. If all four cylinders dump their exhaust into a single pipe, the pressure wave from cylinder 1 would interfere with the evacuation of cylinder 3. The gases would collide, causing turbulence and lag. To solve this, Toyota utilizes a twin-scroll design within that integrated head. The exhaust ports for cylinders 1 and 4 are channeled into one scroll, while cylinders 2 and 3 feed another. These two streams of high-velocity gas never touch until they strike the turbine wheel. This separation ensures that the exhaust pulses arrive in a rhythmic, uninterrupted hammer-blow cadence, keeping the turbo spinning efficiently even at lower RPMs. It turns chaos into a synchronized attack on the turbine blades. Moving deeper into the engine, we must address the structural violence occurring at the bottom end. The crankshaft is the backbone of the engine, converting the linear motion of the pistons into rotational force. At 600 horsepower, the torsional stress on the crankshaft is immense. It wants to twist like a wet towel. Standard cast iron crankshafts would snap under this torque. Toyota's blueprints suggest the use of a forged steel crankshaft, balanced to a degree usually reserved for aerospace components. But the real innovation is in how they manage the inherent flaw of the inline-4 engine: secondary vibration. Inline-4 engines naturally vibrate at twice the frequency of the engine rotation. This secondary imbalance creates a harsh buzzing that can rattle a car apart and, more critically, foam the engine oil. To counter this, Toyota has integrated a complex module of twin balance shafts located in the oil pan. These heavy steel shafts spin at twice the engine speed in the opposite direction of the vibrations. They are cancellation devices, using physics to neutralize the shaking forces generated by the pistons. In a race car, you might delete these to save weight and reduce parasitic drag. But Toyota engineers managed to mount these shafts on low-friction needle roller bearings, ensuring the engine remains smooth enough for a street car without sacrificing the precious horsepower usually lost to spinning heavy weights. Then there are the connecting rods, the arms that connect the pistons to the crankshaft. These are the components most likely to fail in a high-horsepower build. They are subjected to compressive forces during combustion and stretching forces during the exhaust stroke. Toyota employs a manufacturing technique called fracture splitting. The connecting rod is forged as one single piece, and then the bottom cap is literally snapped off, fractured, at a microscopic level. When the rod is bolted onto the crankshaft, the jagged, unique fracture surfaces lock together perfectly, providing a stronger, more rigid bond than any machined surface could achieve. This prevents the rod cap from walking or shifting under the extreme 600 horsepower load. It is a brutal, yet elegant, manufacturing solution to a physics problem. While the metal components provide the strength to survive the explosion, the engine's longevity relies entirely on its circulatory system, the oil. In a standard vehicle, the oil pump is a simple mechanical slave to the crankshaft. The faster the engine spins, the faster the pump spins, and the higher the oil pressure rises. This sounds logical, but it is actually inefficient. At cruising speeds on a highway, the engine is spinning fast but under low load, yet a traditional pump is blindly forcing high-pressure oil through the system, wasting horsepower to churn fluid that isn't needed. Conversely, at low RPMs with high turbo boost, a common scenario for this torque-heavy 2.0-liter, the engine needs massive oil pressure to protect the bearings, but a standard pump is spinning too slowly to provide it. Toyota's engineering team solved this paradox with a continuously variable displacement oil pump. This is not a static device. It is a smart component with a variable internal chamber. The engine control unit, ECU, monitors load, temperature, and throttle position, and physically alters the geometry of the pump mechanism. It can command high pressure at low RPMs to protect the crankshaft bearings during a hard launch, or it can dial back the pressure at high-speed cruising to reduce parasitic drag. It ensures that the engine only uses the exact amount of energy required to lubricate itself, saving crucial horsepower that would otherwise be lost to hydraulic resistance. This intelligent lubrication system feeds into another critical defense mechanism: under-piston oil jets. With combustion temperatures hot enough to soften aluminum, the pistons are in constant danger of thermal failure. To combat this, Toyota installed high-velocity nozzles at the base of each cylinder. These are not for lubrication, they are for cooling. They spray a continuous stream of oil directly onto the underside of the piston crown. This oil acts as a heat sink, pulling thermal energy away from the combustion surface and carrying it down into the oil pan to be cooled. It allows the piston to survive in a thermal environment that would otherwise melt a hole straight through the center. The management of heat extends beyond the oil. The cooling system itself has been completely digitized. The days of the simple wax thermostat, a passive valve that opens when hot and closes when cold, are over. This engine utilizes a multi-way flow control valve. This is a computer-controlled rotary valve that acts like a traffic cop for the coolant. It can send water only to the cylinder head to cool the combustion chambers while blocking flow to the block to speed up warm-up. It can direct flow to the heater core for the cabin or bypass the radiator entirely. This allows the engine to maintain a thermal sweet spot. Engines are most efficient at a very specific temperature. Run them too cold and the oil is too thick. Run them too hot and you risk detonation. This system keeps the engine within 1 degree of its optimal operating temperature, regardless of whether the car is sitting in traffic or tearing down a racetrack. Furthermore, the water pump itself is electric. By removing the mechanical link to the engine belt, Toyota eliminates another source of parasitic drag. But the real benefit is after-run cooling. When a 600 horsepower engine is shut off immediately after a hard run, the heat trapped inside the metal has nowhere to go. This heat soak can cook the oil and damage the turbo bearings. The electric water pump solves this by continuing to circulate coolant even after the engine is turned off, slowly bringing the temperature down and preventing the oil from coking inside the turbo lines. It is a feature designed not for the dyno sheet, but for the lifespan of the machine. All of these systems, the variable oil pump, the split cooling, the direct injection, the friction reduction, coalesce into a single metric that engineers obsess over: thermal efficiency. For over a century, the internal combustion engine was woefully inefficient, wasting roughly 70 to 75% of the energy in gasoline as heat and noise, utilizing only 25 to 30% to actually turn the wheels. Toyota's new 2.0-liter architecture pushes this number into the realm of science fiction, aiming for and exceeding 40% thermal efficiency. In the world of thermodynamics, this is a monumental leap. It means they are extracting more mechanical work from every drop of fuel than almost any other gasoline engine in history. They aren't just making power, they are wasting less. With the mechanical architecture capable of withstanding the pressure and the thermal management system keeping the metal from melting, the focus shifts to the moment of truth, the ignition. In a standard engine, a spark plug is a simple device. It acts like a lighter, providing a small arc of electricity to start the fire. But inside Toyota's 600 horsepower chamber, the environment is hostile to electricity. The immense pressure generated by the turbocharger and the compression stroke creates an atmosphere so dense that it acts as an insulator. In physics, as air pressure rises, the voltage required to jump a spark gap increases exponentially. A standard ignition coil would fail here. The spark would simply be blown out, like a candle in a hurricane, resulting in a misfire and instant loss of power. To overcome this, Toyota has implemented a high-energy multi-strike ignition system. The ignition coils sitting on top of the valve cover are not standard automotive parts. They are akin to small power plants. They are capable of generating voltages far exceeding the typical 30,000 volts found in road cars. But voltage is only part of the solution. The duration of the spark is critical. The system utilizes multi-strike logic, where the spark plug does not fire just once per cycle. Instead, during the milliseconds of the compression stroke, the plug fires a rapid-fire burst of 3 to 4 distinct electrical arcs. This ensures that even if the violent turbulence of the intake charge extinguishes the first spark, the second or third will successfully ignite the mixture. It guarantees combustion stability at 7,000 revolutions per minute, where the window for ignition is measured in microseconds. The spark plugs themselves are marvels of material science. Standard copper or platinum plugs would erode within minutes under this intensity. The electrodes are tipped with ruthenium, a rare transition metal that offers even higher heat resistance and durability than iridium. The shape of the electrode is needle-fine, designed to minimize quenching, where the cold metal of the plug itself sucks the heat out of the initial flame kernel, killing the fire before it spreads. This tiny, exotic piece of metal is the spear tip of the entire operation, enduring temperatures of 2,500 degrees Celsius dozens of times per second. Governing this chaotic symphony of fire, pressure, and metal is the engine control unit, ECU. In the past, ECUs were simple computers that looked up data on a spreadsheet. If the engine was at 3,000 revolutions per minute and 50% throttle, the computer would look at a pre-programmed table to decide how much fuel to inject. That approach is too slow and too crude for this level of performance. Toyota's new engine utilizes model-based control. The ECU contains a complex mathematical model, a digital twin, of the engine running inside its processor. It doesn't just look up values, it solves physics equations in real time. This digital brain constantly calculates the estimated air mass, the predicted cylinder pressure, and the exact flame propagation speed based on current conditions. If the driver fills up with lower quality gasoline, the ECU doesn't just wait for the engine to knock. It predicts the likelihood of knock based on the fuel's chemical properties and proactively adjusts the timing to protect the engine while maintaining maximum possible power. It is a predictive system rather than a reactive one. It listens to the engine using wideband piezoelectric knock sensors bolted to the block. These sensors are tuned to ignore the natural mechanical noise of the valves and injectors, listening exclusively for the specific resonant frequency of detonation, the sound of the engine destroying itself. The ECU effectively rides the knock limit. To get maximum efficiency and power, you want to ignite the fuel as early as possible. However, ignite it too early, and the pressure spikes before the piston reaches the top, hammering it backward and destroying the rod bearings. The ECU keeps the timing on a razor's edge, advancing the spark until it detects the microscopic vibration of incipient knock, and then pulling it back instantly. It is a game of chicken played with the laws of physics, executed thousands of times per minute. This level of computational control allows Toyota to run a high compression ratio on a turbocharged engine, something that was previously considered a mechanical contradiction. Furthermore, this digital integration extends to the wastegate control of the turbocharger. In older turbocharged cars, the wastegate, the valve that releases excess exhaust pressure, was controlled by a vacuum hose. It was a pneumatic, analog system that was often spongy and imprecise. Toyota uses an electronic wastegate actuator. The ECU can clamp the wastegate shut to build boost instantly or feather it open to bleed off pressure with surgical precision. This allows for boost scavenging strategies, where the engine intentionally keeps the wastegate open during cruising to reduce back pressure, simulating a larger, naturally aspirated engine for better fuel economy, then snaps it shut the nanosecond the driver demands power. The immense power of this 2.0-liter engine is not just about explosions, it is about what happens after the explosion. In the history of automotive engineering, emissions equipment has always been the enemy of performance. Devices like catalytic converters and exhaust gas recirculation, EGR, valves were mandated by governments to save the polar bears, but they notoriously strangled engines, clogging intakes with soot and reducing horsepower. However, Toyota's engineers have performed a kind of mechanical judo with the new 2.0-liter architecture. They haven't just tolerated these emissions systems, they have weaponized them to increase performance. The key lies in a system called cooled low-pressure EGR. In a standard engine, EGR takes hot, dirty exhaust gas and dumps it back into the intake. It's like asking a runner to breathe through a straw while inhaling their own breath. It kills power. Toyota's system is different. It pulls the exhaust gas from after the particulate filter, where it is clean, and runs it through a dedicated, high-efficiency water-to-air cooler. By the time this gas re-enters the engine, it is cold. Why would you want to put inert gas into a 600-horsepower engine? Because nitrogen and carbon dioxide are excellent heat absorbers. When this cold, inert gas enters the combustion chamber, it doesn't burn. Instead, it acts as a thermal buffer. It absorbs the peak heat of the combustion spike, lowering the overall cylinder temperature just enough to prevent the nitrogen in the air from turning into NOx, pollution, but more importantly, it prevents the fuel from self-detonating knock. This allows the engineers to advance the ignition timing further than would be possible with pure air. They are using pollution control hardware to unlock more horsepower. It is a paradox. The cleaner the engine runs, the faster it goes. To facilitate this complex breathing, Toyota had to rethink the physical construction of the intake and exhaust ports. In a traditional cylinder head, steel valve seats are pressed into the aluminum head. These steel rings create a bottleneck, They are thick and disrupt the smooth flow of air. They also act as thermal barriers, preventing heat from escaping the valves into the cooling jacket. For this flagship engine, Toyota deleted the pressed-in seats entirely. Instead, they utilized a technique known as laser-clad valve seats. Using a high-powered industrial laser, a stream of copper alloy powder is melted directly onto the aluminum head, creating a valve seat that is chemically bonded to the block. This layer is microscopically thin. The result is a throat opening that is significantly larger, allowing for a massive increase in airflow volume without increasing the size of the head. Furthermore, because the alloy is bonded directly to the aluminum, heat transfer is improved by 400%. The heat from the exhaust valves is sucked away into the coolant almost instantly. This technology, once the exclusive domain of Formula One and Le Mans prototypes, is now the standard for Toyota's highest-performing road engine. It ensures that the valves don't melt even under the sustained thermal load of 300 horsepower per liter. Then there is the issue of the red line. A long-stroke engine typically hits a wall at 6,000 revolutions per minute because the pistons are moving too fast. However, the soundtrack of this engine tells a different story. It revs freely to 8,000 revolutions per minute. How? The secret is in the lightweight reciprocating assembly. Every gram of weight on the piston or connecting rod multiplies exponentially as RPM rises. Toyota used 3D modeling topology optimization to remove material from the pistons and rods in areas where stress was low. They shaved off grams here and milligrams there, resulting in a piston assembly that is 20% lighter than a standard unit. This reduction in reciprocating mass reduces the inertia at the top and bottom of the stroke. The engine doesn't fight itself to change direction. This allows the long-stroke design to rev like a short-stroke motorbike engine. The result is a power band that is impossibly wide, massive torque from the electric turbo down low, and screaming horsepower from the lightweight internals up high. It eliminates the need to constantly shift gears to stay in the power. The power is everywhere. But creating this power is only safe if you can monitor it. Embedded deep within the block are sensors that didn't exist in consumer cars a decade ago. We're talking about in-cylinder pressure sensors. Usually, an engine guesses how much pressure is in the cylinder based on airflow and fuel calculations. This engine measures it directly. These sensors provide real-time feedback to the ECU, allowing it to balance the power output of each individual cylinder. If cylinder number 3 is running 1% weaker than cylinder number 1, the computer adjusts the fuel trim for that specific injector to compensate. The engine is constantly self-balancing, ensuring that the crankshaft receives a perfectly smooth delivery of torque, reducing vibration and wear on the bearings. To power the electrically assisted turbocharger and the high-speed valve actuators, the engine relies on an electrical backbone that far exceeds the capabilities of a standard car battery. A traditional 12-volt system is simply too weak. It cannot deliver the sudden, massive surge of current required to spin a turbo compressor from 0 to 100,000 revolutions per minute in under a second. To solve this, Toyota integrated a 48-volt electrical architecture. This is not to be confused with a plug-in hybrid system that drives the wheels. This is a support grid dedicated exclusively to the engine's high-demand peripherals. A compact 48-volt lithium-ion battery is tucked away in the chassis, separate from the main starter battery. This dense energy reserve acts like a capacitor, ready to dump huge amounts of energy into the electric turbo the moment the driver demands power. It also powers the water pump and the air conditioning compressor, removing all belt-driven accessories from the crankshaft. This beltless design is crucial. In a traditional engine, the serpentine belt drags on the engine, stealing roughly 5 to 8 horsepower. By electrifying these components, that parasitic loss is eliminated, sending that power directly to the tires instead. Moving upstream from the engine block, we encounter the intake manifold. In most modern cars, this component is made of injection-molded plastic. It's cheap, light, and effective for daily driving. However, at 600 horsepower, the boost pressure is high enough to literally blow a plastic manifold apart at the seams. Aluminum was the old-school alternative, but it suffers from heat soak. It absorbs the heat of the engine bay and transfers it into the intake air, reducing density and power. Toyota's solution is a material borrowed from the aerospace industry, carbon fiber reinforced polymer, CFRP. The intake plenum is molded from layers of carbon fiber. This material offers the tensile strength of steel to contain the massive boost pressure, but has the thermal conductivity of wood. It acts as an insulator. Even if the engine bay is scorching hot, the air inside the carbon plenum remains cool. Furthermore, the interior of the manifold is polished to a mirror finish. This reduces air resistance to near zero, ensuring that the air velocity generated by the turbo is maintained all the way to the intake valves. The shape of the runners is tuned using Helmholtz resonance principles. At specific RPMs, the pressure waves bouncing inside the tubes synchronize with the opening of the valves, essentially ramming extra air into the cylinder without the turbo having to work harder. It is natural supercharging through acoustics. Speaking of acoustics, the sound of a four-cylinder engine has historically been its weak point. V8's rumble, V12's scream, for cylinders typically drone. To change this perception, Toyota's engineers treated the exhaust system like a musical instrument. They utilized an active exhaust valve system, but with a level of granularity usually seen in high-end audio equalizers. The muffler contains multiple chambers and bypass valves that are controlled by the ECU. At low RPMs, the valves close, forcing the exhaust through baffles to eliminate the low-frequency drone that plagues large displacement four cylinders. But when the throttle opens, the valves bypass the muffler entirely. The length of the exhaust piping was calculated to emphasize specific odd-order harmonics. The result is not the flat buzz of a generic tuner car. It is a raw, jagged snarl that resembles a World Rally car. The firing order, combined with the twin-scroll manifold, creates a pulsing rhythm that sounds distinctively aggressive. They didn't just want the engine to perform, they wanted it to have presence. Connecting this powerhouse to the transmission presented another challenge: vibration. A high compression, four-cylinder engine produces violent torsional spikes with every power stroke. These spikes can shatter transmission gears. To smooth this out, Toyota employed a dual-mass flywheel of immense complexity. Instead of a solid steel disc, the flywheel consists of two plates connected by a series of heavy-duty springs and dampeners. It absorbs the shock of each combustion event before it reaches the gearbox. This allows the driver to experience the raw power of the engine without the driveline shudder that usually accompanies high-torque four-cylinder race engines. It effectively filters the violence of the explosion into smooth rotational force. But perhaps the most subtle innovation is the smart alternator. In a race for efficiency, constantly charging the battery is wasteful. This alternator contains a clutch mechanism. During acceleration, the alternator disconnects completely, freeing the engine from its magnetic drag. It only engages to charge the battery when the car is coasting or braking. This system, known as micro-regeneration, ensures that during a full-throttle run, 100% of the engine's energy is focused on acceleration, with zero parasitic loss to the electrical system. It is the final percentage point of efficiency that separates a good engine from a world record holder. The existence of such a complex machine raises a fundamental question: reliability. In the world of high-performance tuning, it is accepted that a 600 horsepower, 2.0-liter engine is a glass cannon, powerful but fragile, requiring rebuilds every few thousand miles. Toyota, however, cannot sell a glass cannon. Their brand reputation is built on the bedrock of unkillable machinery. To reconcile these opposing forces, extreme performance and extreme durability, the development process for this engine did not begin in a foundry. It began in a server room. Long before a physical prototype was ever assembled, Toyota created a digital twin. This was a complete, molecule-by-molecule virtual simulation of the engine. Using supercomputers, they ran this virtual engine for the equivalent of 1 million miles. They simulated the worst possible conditions, towing a heavy trailer up a mountain in Death Valley heat, followed instantly by a cold start in the Arctic Circle. The simulation allowed them to see inside the solid metal, visualizing stress fractures before they could happen in reality. They could watch how the cylinder walls expanded at 8,000 revolutions per minute and adjust the casting molds by microns to compensate. This fail-fast digital strategy meant that when they finally built the physical engine, it was already generation 5.0. But simulations are only math. Reality is the final judge. The physical prototypes were subjected to what engineers call the hell cycle. In a sealed, soundproof bunker, the engine was mounted to a dynamometer and programmed to run at its maximum redline, 8,000 revolutions per minute. Not for minutes, but for 24 continuous hours. The exhaust headers glowed a translucent, angry orange, radiating enough heat to melt plastic 10 feet away. The turbocharger spun at 150,000 revolutions per minute, a screaming banshee of compressed air. Most racing engines would disintegrate after 4 hours of this abuse. The Toyota unit survived, proving that the oil and cooling systems were not just effective, but over-engineered. A critical weak point in any high-boost engine is the head gasket, the seal between the engine block and the cylinder head. Under 300 bar of cylinder pressure, the head literally tries to lift off the block, blowing the gasket and mixing oil with coolant. To prevent this catastrophe, Toyota developed a proprietary stopper layer multilayer steel, MLS gasket. Standard MLS gaskets are flat sheets of steel stacked together. The stopper layer features a folded, reinforced ring directly around the cylinder bore. This acts like a metal O-ring, biting into the head and block to create a seal that gets tighter as pressure increases. It effectively fuses the top and bottom of the engine into a single pressure vessel. The torture testing didn't stop at high RPMs. They subjected the block to thermal shock. This involves running the engine until it reaches its peak operating temperature, then instantly flushing the cooling system with coolant chilled to -40 degrees Celsius. The sudden thermal contraction causes metal to shrink violently. If there were any flaws in the casting or the alloy mix, the block would crack like a dropped dinner plate. Toyota repeated this cycle thousands of times. The secret to surviving this lies in the bedplate architecture. Instead of individual main bearing caps holding the crankshaft in place, the bottom half of the engine block is a single, massive casting called a bedplate. This integrates all the main caps into one rigid structure. It creates a ladder frame that reinforces the bottom of the block, preventing it from twisting or warping under thermal shock. It adds weight, yes, but it provides the stiffness of a diesel truck engine to a high-revving sports car motor. This obsession with durability is directly linked to the involvement of Gazoo Racing, GR, Toyota's motorsport division. This engine wasn't designed by the committee that builds the Corolla. It was spearheaded by the team responsible for the World Rally Championship, WRC victories. In WRC, cars launch off jumps, slam into gravel, and run flat out through forests. The engine is a structural member of the chassis, taking physical hits. The data from the rally stages, vibration frequencies, G-force oil starvation, impact loads, was fed directly back into the road car development. For instance, the oil pickup tube, the straw that sucks oil from the pan, was redesigned based on telemetry from a rally car that landed a jump awkwardly and starved the engine of oil for 0.5 seconds. The new design features a baffled trapdoor system that keeps the pickup submerged in oil, even if the car is upside down or pulling 2G in a corner. This is what they mean by born on the track. It isn't marketing fluff. It is engineering evolution driven by the harshest environment on Earth. Even the fasteners, the bolts holding the engine together, are special. Standard bolts stretch slightly when tightened. For this application, Toyota utilizes torque-to-yield bolts made from a high-tensile alloy. When tightened, these bolts are stretched to their plastic deformation point, acting like extremely stiff springs. This ensures that the clamping force remains constant even as the aluminum engine expands and contracts with heat. It is a one-time use fastener system that guarantees the engine stays sealed tight, no matter how hard it is driven. A 600 horsepower engine is useless if the transmission attached to it explodes. The violence of a high-boost 2.0-liter engine is distinct from the smooth power delivery of a V12. The torque comes in sudden, sledgehammer-like spikes. Standard automatic transmissions, with their fluid-filled torque converters, are designed to slip and smooth out these shifts. But slip is the enemy of speed. On the other hand, dual-clutch transmissions, DCTs, are lightning fast but notoriously fragile in stop-and-go traffic, often overheating or shuddering. Toyota needed a third option, something that combined the durability of a tank with the snap of a rifle bolt. Enter the direct automatic transmission, DAT. This is an 8-speed gearbox that rewrites the logic of shifting. In a traditional automatic, the torque converter does most of the work, using fluid dynamics to transfer power. In the DAT, the torque converter is largely vestigial. It is only used for crawling at 2 miles per hour. The moment the car is moving, a massive multi-plate lockup clutch engages, mechanically fusing the engine to the wheels. There is no fluid slush. There is only a direct metal-to-metal connection. The brain of this transmission is equally impressive. It doesn't just monitor speed and throttle position, it monitors the driver's behavior. Using input from the brake pressure and steering angle sensors, The transmission knows you are approaching a corner before you even downshift. It anticipates the G-force. If you brake hard for a hairpin, the DAT aggressively downshifts 3 gears instantly, holding the RPMs exactly in the meat of the power band, 4,500 to 7,000 revolutions per minute, so that when you get back on the gas, the turbo is already spooled and the car rockets out of the corner. It shifts faster than a human can think, yet it doesn't have the fragile, glass-jaw reliability of a dual-clutch unit. But the most revolutionary aspect of this engine platform is not visible on the dyno sheet. It is a secret hidden in the chemical compatibility of its components. We live in an era where governments are effectively banning the internal combustion engine. Most manufacturers are pivoting entirely to electric vehicles, EVs. Toyota, however, is playing a different game. They call it the multi-pathway strategy. This 2.0-liter engine is not designed just for gasoline. It is an omnivore. The fuel system, from the tank lines to the high-pressure seals in the injectors, has been engineered to resist the corrosive nature of carbon-neutral fuels, e-fuels, and high-ethanol blends. E-fuels are synthetic hydrocarbons created by capturing CO2 from the atmosphere and combining it with hydrogen. They burn like gas but are carbon-neutral. Standard rubber seals and aluminum lines degrade rapidly when exposed to these chemically aggressive fuels. Toyota's engineers used fluoroelastomer seals and specialized stainless steel alloys throughout the fuel path. This engine is future-proofed. It is designed to run on fuels that don't even exist at scale yet, ensuring that when the oil wells run dry or are legislated out of existence, this machine will still be roaring down the track. This adaptability extends to the combustion chamber itself. The high tumble flow and the advanced ignition system we discussed earlier are perfectly suited for burning lean mixtures of hydrogen. While this specific block is set up for liquid fuel, the architecture shares its DNA with Toyota's experimental hydrogen combustion prototypes. The spacing of the head bolts, the thickness of the cylinder walls, and the cooling jackets are all over-engineered specifically so that, with a head swap and new injectors, this same bottom end could theoretically burn hydrogen gas. It is a bridge between the fossil fuel past and a clean future, without losing the soul of the piston engine. This philosophy comes directly from the top. Akio Toyoda, the former CEO and current chairman, is a master driver who races under the pseudonym Marizo. He famously stated that carbon is the enemy, not the internal combustion engine. This 2.0-liter project is his manifesto. It is a statement that efficiency and emotion do not have to be sacrificed on the altar of electrification. By achieving 40% plus thermal efficiency, this engine rivals the carbon footprint of an EV when charged on a coal-heavy power grid, but it does so while weighing 500 pounds less than a battery pack. The integration of the engine into the chassis also features a novel structural mounting system. Usually, engines hang on rubber mounts to isolate vibration. In this application, the engine mounts are active, fluid-filled dampers that stiffen up under cornering loads. The engine block effectively becomes a stress-bearing member of the car's frame, increasing the torsional rigidity of the entire vehicle. When you turn the steering wheel, you aren't just turning the suspension, you are leveraging the mass of the engine to help rotate the car. It is a holistic approach where the power plant and the chassis are no longer separate entities. They are a single, fused organism. The implications of this engine extend far beyond the racetrack or the enthusiast's garage. We must consider the industrial scalability of what Toyota has achieved. Typically, an engine with this level of specific output, 300 horsepower per liter, is a boutique item, hand-built by artisans in a clean room, costing upwards of $50,000 per unit. Think of the engines in a McLaren or a Ferrari. They are masterpieces, but they are impossible to mass-produce. Toyota, however, is the master of Kaizen, continuous improvement and efficiency. The true genius of this 2.0-liter project is that it is designed to be built on a standard assembly line. To achieve this, Toyota revolutionized the casting process itself. The complex water-jacketed exhaust manifold and the tumble port intake runners are incredibly difficult to cast using traditional sand molds, which often leave rough surfaces and variances. Toyota implemented a technique called high-speed inorganic 3D printed sand casting. Instead of using wooden patterns to make the sand molds, giant 3D printers lay down layers of sand bound by an inorganic, water-soluble binder. This allows for geometries that are physically impossible to machine, internal curves and undercuts that guide airflow and coolant with mathematical perfection. Once the metal is poured and cools, the sand is simply washed away with water, leaving a pristine, complex aluminum structure. This brings Formula One casting technology to a price point compatible with a mass-market sports car. Furthermore, the modular displacement concept comes into play. While we're focusing on the 2.0-liter monster, the architecture is scalable. By slicing off a cylinder, it becomes a 1.5-liter three-cylinder, the engine found in the GR Yaris. Add 2 cylinders, and it becomes a 3.0-liter inline six. The pistons, rods, valves, and combustion chamber design are identical across the family. This shares the R&D costs across millions of vehicles. The technology developed to keep the 600 horsepower version from exploding. The DLC coatings, the laser-clad valve seats, the split cooling, trickles down to the economy engines, making them more efficient and durable. You aren't just buying a race engine. You are buying a piece of a master plan to elevate the entire Toyota lineup. Let's talk about the sound again, but from a physics perspective. High-power four-cylinder engines often suffer from boominess or resonance inside the cabin that can be nauseating. Manufacturers usually pump fake engine noise through the speakers to mask this. Toyota refused. They installed a mechanical sound composer. This is a dedicated tube connecting the intake plenum directly to the firewall of the cabin. It contains a diaphragm that vibrates with the pulses of the intake air. When the throttle body snaps open, the driver hears the genuine, raw induction noise, the sound of air rushing into the engine, amplified naturally. It creates a visceral connection between the driver's right foot and the engine's lungs, without using a single microchip or speaker. The maintenance aspect of such a high-stress machine was also reimagined. In a Ferrari, a major service might require dropping the entire engine subframe. Toyota engineers designed this 2.0L block with serviceability access points. The oil filter, the high-pressure fuel pump, and the alternator are all located on the cold side, or the front of the engine, reachable without removing the intake manifold or the turbo. The electric water pump is mounted externally. They respected the mechanics who will eventually work on these cars 10 years from now. It is a high-performance engine designed for the real world, not just for the warranty period. The crowning jewel of the auxiliary systems is the anti-lag system, ALS. In rally cars, ALS works by dumping raw fuel into the hot exhaust manifold, causing explosions that keep the turbo spinning when the driver lifts off the gas. It sounds like gunshots and destroys the turbocharger in short order. Toyota's street-legal version is smarter. It uses the electric motor on the turbo shaft, which we mentioned earlier, to harvest energy. When the driver lifts off the throttle to brake for a corner, the electric motor reverses its function, acting as a generator. It creates drag on the turbo, slowing it down but generating electricity to recharge the 48-volt battery. Then, the instant the driver touches the gas, that stored energy is dumped back into the motor to spin the turbo up instantly. It provides the response of a rally anti-lag system with 0 explosions and 0 wear on the components. It is regenerative braking, but applied to the turbocharger instead of the wheels. This system highlights the convergence of digital and mechanical engineering. The software controlling the electric turbo has to be perfectly synced with the fuel injection and the variable valve timing. If they are off by a millisecond, the engine chokes. The calibration of this system took 3 years of dedicated coding. The result is a torque curve that is essentially flat. From 2,500 revolutions per minute to 7,500 revolutions per minute, the engine delivers a constant, relentless wave of force. It doesn't feel like a peaky, stressful race engine. It feels like a massive electric motor that never runs out of breath. To fully appreciate the magnitude of Toyota's achievement, we must look sideways at the competition. For years, the undisputed king of the 2.0-liter world was Mercedes-AMG with their M139 engine. It was a marvel of German engineering, producing over 400 horsepower. It was considered the absolute limit of what a production four-cylinder could do. Toyota didn't just aim to match that benchmark, they vaulted over it. By targeting 600 horsepower, they are entering territory usually occupied by twin-turbo V6s and V8s. They have effectively democratized supercar performance, packaging it into a unit that is cheaper to build, lighter to carry, and easier to service than the exotic multi-cylinder engines of Europe. But the most surprising aspect of this engine is its open invitation to the aftermarket community. Toyota is acutely aware of the cult status of their 1990s icon, the 2JZ GT engine found in the Supra. That engine became legendary not for its stock power, but for its ability to handle double or triple that power without braking. It was an over-engineered block of iron. For this new 2.0-liter project, the engineers seem to have adopted the same philosophy. The cylinder walls are thicker than necessary. The deck is reinforced beyond the requirements of 600 horsepower. They have built what is essentially a tuner's sandbox. Internal documents and patent analyses suggest that the stock 600 horsepower tune is actually conservative. The fuel system has headroom for 20% more flow. The turbocharger is operating within its efficiency island, not at its desperate limit. Toyota knows that the moment this engine hits the streets, tuners will start turning up the boost. Instead of fighting this with locked ECUs and fragile components, they have built a foundation that can likely support 800 or even 1,000 horsepower with modifications. They are not just selling a car, they are handing the keys to a new generation of hot rodders, providing a canvas for mechanical creativity that has been vanishing in the modern era. However, power is nothing if you can't drive the car legally. The specter haunting every combustion engine today is Euro 7, the upcoming European emissions standards that are so strict they were expected to kill the gasoline engine entirely. Toyota's solution to Euro 7 is a masterclass in thermal manipulation. The hardest part of emissions testing is the cold start, where the catalytic converter is too cold to work. In a normal car, you just idle high and wait. Toyota uses the electric turbocharger to solve this. Upon startup, the electric motor spins the turbo to generate boost against a closed throttle valve. This creates artificial load on the engine, forcing it to work hard even while sitting in neutral. This generates massive amounts of heat instantly. Simultaneously, the variable valve timing opens the exhaust valves early, dumping this hot fire directly into the catalytic converter. The result? The emission system reaches operating temperature in seconds rather than minutes. They are using the electric turbo not for speed, but as a heater. It allows a 600 horsepower monster to pass emissions tests designed for a hybrid city car. The physical packaging of the engine also hints at the cars it is destined for. The engine is remarkably short and compact. The lack of external exhaust manifolds and the integration of accessories mean it can be mounted further back in the chassis. This is crucial for the front midship layout, where the engine sits behind the front axle, but in front of the driver. This centers the mass of the car, reducing the polar moment of inertia. In plain English, it makes the car rotate instantly when you turn the wheel. But the rumors point to something even more exciting, a mid-engine revival. The compact dimensions of this 2.0-liter unit make it the perfect candidate for a successor to the legendary Toyota MR2. Imagine a lightweight, two-seater sports car with 600 horsepower sitting directly behind your spine. The power-to-weight ratio would rival hypercars costing 10 times as much. By shrinking the engine while increasing the power, Toyota has given their chassis designers the freedom to build cars with perfect 50-50 weight distribution, uncompromised by a heavy V8 or a massive battery pack. Finally, we must touch on the transmission cooling. A 600 horsepower engine generates enough heat to boil transmission fluid in minutes on a track. Toyota has integrated a heat exchanger that links the transmission oil loop directly to the engine's main cooling circuit. But it's bidirectional. During a cold start, the engine coolant warms up the transmission fluid to reduce friction. Once the track session begins, the massive radiator capacity of the engine is used to cool the gearbox. It is a symbiotic relationship. They have eliminated the need for heavy, separate transmission coolers, saving weight and reducing complexity. It is yet another example of how every system in this car talks to every other system. As we stand at the crossroads of automotive history, the significance of Toyota's new 2.0-liter engine becomes clear. It is not just a collection of pistons, valves, and sensors. It is a declaration of defiance. In a world rushing headlong towards silent, digitized transportation, Toyota has planted a flag in the ground for the internal combustion engine. They have proven that the technology is not dead. It was merely waiting for a revolution in physics and material science to awaken it from its slumber. By achieving thermal efficiency numbers that were once thought theoretically impossible, they have created a machine that is as environmentally conscious as it is exhilarating. This engine is poised to become the 2JZ of the modern era. Just as the iron block straight six of the 1990s defined a generation of tuners and racers, this 2.0-liter, 600 horsepower marvel will likely define the next 30 years of automotive performance. It offers a bridge between the analog past we love and the high-tech future we face. It combines the raw, visceral engagement of fire and noise with the digital precision of 48-volt systems and artificial intelligence. It is the perfect synthesis of man and machine. What Toyota has built is a halo engine, a technological masterpiece that casts a glow over their entire brand. It reminds us that the company that gave us the Prius, the ultimate appliance, is also the company that gave us the LFA, the ultimate exotic. It shows a duality that few other manufacturers possess, the ability to save the planet on Monday and set a lap record on Sunday. This engine is destined to find its home in the rebirth of icons. Rumors of a new Celica GT4 or a mid-engine MR2 are no longer just whispers. They are mechanical inevitabilities waiting for this heart to be transplanted into them. But perhaps the most important takeaway is this: Toyota didn't have to do this. It would have been easier, cheaper, and safer to simply buy batteries and electric motors like everyone else. Developing a clean-sheet, high-performance combustion engine in the 2020s is a massive financial risk. It is a passion project authorized by car enthusiasts for car enthusiasts. It validates every petrolhead who has ever looked at an EV and felt that something was missing: the soul, the vibration, the mechanical sympathy. So, as we close the blueprints on this engineering miracle, we are left with a single powerful thought. The internal combustion engine is not going gently into that good night. It is raging against the dying of the light, screaming to 8,000 revolutions per minute with 600 horsepower, fueled by innovation and a refusal to compromise. Toyota has bent the laws of physics not just to move a car, but to move us. This is the end of our deep dive into the secrets of Toyota's 2.0 L Monster. If you enjoyed unraveling this engineering mystery with us, please make sure you are subscribed to the channel. We are on a mission to decode the most fascinating machines on Earth, and we can't do it without you. Hit that notification bell so you never miss a teardown. And I want to hear from you in the comments. Is this engine the savior of the sports car, or is it the last gasp of a dying dinosaur? Let the debate begin below. Thank you for watching, thanks for your support, and as always, keep the rubber side down. See you in the next one.